Hello friends, welcome to engineering tutorial. So we will continue our discussion with electrical machines, and so far we have discussed some basic introductory concepts related to transformers, and we have discussed about ideal transformer in no load condition. And also we have discussed some concepts related to transformer operation, which is related to network theory, that is coupled circuits, and phasor diagrams for circuits involving resistors, inductors and capacitors. So you please check out those videos first before watching this video. Okay. So we all know that a transformer is an electrical machine which performs energy conversion, which can increase or decrease the input AC supply voltage value without any direct electrical connection. It operates on the principle of Faraday's law of electromagnetic induction and Lenz's law. So we have already discussed about the general concept of transformer. So ideal transformer. So an ideal transformer is one which has no winding resistance. So this is an ideal transformer in no load condition. We have the laminated magnetic core, primary winding, secondary winding, input AC connected to the primary winding. So you can see here it has no winding resistance. So the coil, this primary and secondary windings, they are generally represented by a RL circuit, which means a resistor in series with an inductor. But in ideal transformer, that is, the resistance part is neglected. Okay, and we have also discussed about leakage flux and mutual flux in the coupled circuits, and also in the discussion related to ideal transformer. So ideal transformer has no leakage flux, only mutual flux, and it has no iron losses. Okay, eddy current, hysteresis, like that. But it is it is impossible to design an ideal transformer. Okay, it is impossible to design such a transformer which has no winding resistance, no leakage flux, no iron losses. In reality, there will be winding resistance, there will be leakage flux, not only mutual flux, there will be leakage flux, and there will be losses because of eddy currents, hysteresis, the iron losses. But why this concept of ideal transformer is studied? Because so as to have a reference in our mind, a model, a reference model to compare the performance of actual transformers for that purpose. So this is an ideal transformer in no load. We have already discussed it, and this is the phasor diagram of such a transformer. Okay, we will not discuss all this because we have already discussed it in the previous video. Now let us discuss ideal transformer on load. The difference between this diagram and this diagram is this load impedance connected, ZL, across the secondary winding at the output side. Okay, so here the discussion will start like this. This load which is connected across the secondary winding, it is an inductive load, and it has some amount of resistance associated with it. So we can write the load impedance ZL as RL plus JXL, where XL is inductive reactance, RL is the load resistance, XL is omega L. Okay, XL is omega L. Okay, or J omega. XL is not J, the imaginary part comes in the inductance part, but XL is omega L. But this J, it is the imaginary component. The basic AC circuit concepts. Now, because of this load, okay, a secondary current I2 flows in this direction, which was absent in the no load ideal transformer. No current, because it was open circuited, no current. So here, because of this flow of this secondary current, a situation develops. Okay, so the value of this current is simply E2 by ZL or V2 by ZL, because E2 is equal to V2, where E2 is the secondary induced EMF. Okay, so the situation which develops here is that this secondary current I2, it sets up a magnetomotive force, MMF. We know magnetomotive force is just the product of the number of turns of the coil and the current flowing through the coil. That is called as magnetomotive force. It is similar to electromotive force for electrical circuits. MMF or magnetomotive force in magnetic circuits is the same as electromotive force in electrical circuits. Magnetomotive force drives flux, electromotive force drives current. Okay, I have already discussed these things in our basic concepts related to magnetic circuits, okay, in this electrical machine section. So please check out that video. So this magnetomotive force value N2I2, product of the secondary turns of coil N2 and this secondary current I2, is opposite in nature to the primary MMF, primary magnetomotive force, that is N1I1. Okay, it is opposite in nature. The opposing flux is generated, magnetomotive force. So the nature of I1 is such that the magnetomotive force generated across the primary exactly neutralizes or counterbalances the secondary MMF. Okay, so you got the point here. Because of this load connected, a secondary current I2 flows through the secondary winding. Because of this flow of current, a magnetomotive force called a secondary MMF is generated, which is opposite in nature to the primary magnetomotive force, N1I1. N2I2 is opposite to N1I1. So to counterbalance this secondary MMF, N1I1 is exactly opposite to that of this secondary MMF. So I1, the primary current I1 and the secondary current I2 are anti-phase with each other. They are equal in magnitude but opposite in phase. Okay, so here, for the ideal transformer, the secondary induced EMF E2 is same as V2, that is the first point. There is no voltage drop across the secondary winding resistance because it is an ideal transformer. So no winding resistance, so no voltage drop. That's why E2 is equal to V2. The secondary current sets up this flux which is opposite in nature. To counter that, the primary winding produces a counterbalancing MMF. This primary MMF N1I1 across the primary winding is equal to the secondary MMF N2I2 across the secondary winding. Or we can write I1 as N2 by N1I2, or I1 is equal to KI2, where K is equal to N2 by N1. So depending on the transformer type, whether it is step up or step down transformer, the value of K will control the magnitudes of I1 and I2. But one thing is constant, that is I1 and I2 are anti-phase with each other with a phase difference of 180 degree to produce opposite MMFs or flux. Okay, so that they exactly neutralize each other. And V1 and E1, they are naturally in opposition as per Lenz's law. So the whole operation from start, we know the basic, we have already discussed those things in the basic introductory concepts related to transformer. That is, when a supply V1 is connected, a current I1 flows through the primary winding. This sets up a flux or a magnetomotive force. Because of this flux, this mutual flux which links the primary and the secondary winding, induced EMF is generated E1 as per Faraday's law of electromagnetic induction. By same principle, because of the mutual flux, a secondary induced EMF E2 is also generated, and if we connect a load, we can obtain this output voltage V2. Okay, this is the basic operating principle of a transformer. So for an ideal transformer on no load, this was the phasor diagram. This is the flux phi, V1 and V2. They are separated, or they are 90 degree. They have 90 degree phase difference with respect to the flux, mutual flux. V1 is 90 degree leading, V2 is 90 degree lagging. Now V1 and E1 are in opposition as per Lenz's law. Primary induced EMF and the supply, they are in opposition as per Lenz's law. That also we have discussed. And E2 is equal to V2. That is for ideal transformer in no load condition. So how this will change under loaded condition? So for that, let us have a quick look at the basic RL circuit, which we have already discussed. In the RL circuit, AC supply is connected across R and L, resistor and inductor. The voltage drop across the resistor and inductor are VR and VL respectively. For a purely resistive circuit, voltage drop across resistor and the current, they are in the same phase. VR is equal to IR and I, with I being the reference. Okay, this is for VR and I, voltage drop across a resistor and I. And for a purely inductive circuit, the voltage drop across the inductor is given by I into j omega L, where j omega L is the inductive reactance. So if we draw the phasor diagram for VL and I, VL is 90 degree leading with respect to I. Now combining these two, VR and VL, if we try to draw the phasor diagram for the V, the total voltage, and I, we just have to follow triangle's law of vector addition. VR, VL, these two vectors, this is the resultant vector V. So this is the resultant phasor diagram for V and I. This concept will be utilized here. Here we have connected an inductive load across the secondary winding, which is same as this. RL plus JXL, okay, the inductive load RL plus JXL. So the output voltage V2 and the secondary voltage V2, the output voltage which we get, and the secondary current I2 will follow a similar pattern. See, same, this, all this V1 phi, E1, E2, V2, they are the same as this. Only change is the current. This and this, they are the same, only the difference lies in the current, okay, the direction or the position of the current vectors. See, this is V2, E2 is equal to V2. Here I2 is lagging behind V2 by, let's say, angle phi 2, which lies in between 0 and 90 degree. I1 and I2 are opposite in phase with respect to each other to produce counterbalancing MMFs. Okay, I1 and I2 are antiphase. So I2 is here, I1 will be exactly the opposite. I1, 180 degree phase difference. V1 and V2, they are the same. V1 is leading flux by 90 degree, V2 is lagging behind the flux vector by 90 degree. And V1 and E1, they are in opposition as per Lenz's law. They are equal in magnitude, opposite in phase, and E2 is equal to V2 because there is no winding resistance, secondary winding resistance. So E2 is equal to V2. Okay, so this is the phasor diagram for an ideal transformer under load. So if we take this K value as 1, okay, this K value, if we take it as 1, then we will get this, that is E1 is equal to E2 is equal to V2, because E2 by E1 is equal to 1, E2 is equal to E1. So this is when K is equal to 1, and this is the normal condition, when K has any value other than 1. Okay, so here we have discussed about ideal transformer under load. Okay, this condition. So I want you to watch all the previous videos related to electrical machines where I have discussed about the magnetic circuits, magnetomotive force, flux, reluctance, all of that, and also all the videos related to transformers, the basic introductory concepts about coupled circuits, about phasor diagram for circuits involving resistors, inductors, capacitors, so that you understand this video in a better way. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.